Calculus BC, lesson 4.3. We're going to talk about concavity and do example 3 in our part 2 video. Take a look at the top of the screen. Concavity is really talking about curvature, and it's describing the curvature. Concave up is like a cup. It's kind of got this parabolic shape. It's almost like a little cup shape. Similarly, concave down is like a frown. A great, kind of diagnostic to describe the curvature that a function has. What tells us about concavity? The second derivative. So if the second derivative, f double prime, is going to exist, your function f is concave up if f double prime is positive on that interval. It also means, by the way, that f prime is increasing. If you think about it, we said before, if f prime of x is greater than 0, then f is increasing. We can definitely extend that to say if f double prime of x is greater than 0, then look at this, the function right before it that you would have taken the derivative to get to this second derivative. That would be f prime right here. F prime, we could say, is increasing. So that's another way to write it. Concave down, by way of comparison, that occurs when your second derivative is negative. And that will mean that f prime, similarly, would be decreasing. Here's something super important. The point, meaning you need an x and a y coordinate, c comma f of c, is a point of inflection. It's a point of inflection when you meet these criteria. F is continuous at a particular x value, but there exists a c value, an x value, where the graph is concave up on an interval from a to c and then concave down from C to B, or vice versa. In other words, concavity changes. That's really what you want to see, a change from concave up to concave down, or vice versa. As long as you get a change, f changing from concave down to concave up, or concave up to concave down, we call that point a point of inflection. So let's go ahead and take a look at what used to be a regular staple of a free response on the AP exam. Before calc reform, you'd be given a polynomial, no calculator, and you'd be asked to graph this. In the advent of graphing calculators, this becomes rather simple. You could just type it in. But imagine if we didn't have a graphing calculator. If I said, hey, find the maximum and minimum points. Find out if there's an inflection point. Let's talk about the curvature. Well, here's some review. Let's first talk about extrema. Let's talk about where we might have a relative max or min. We'll have f prime of x would be 3x squared minus 3. We can set that equal to 0. And it does not take long. We can divide by 3, and we just have x squared minus 1. As we'd factor here, we'd have x plus 1, x minus 1, and our critical numbers are going to be x equals negative 1 and x equals positive 1, setting both of these parentheses equal to 0. Well, what do? Well, we go ahead and we make ourselves a number line. And this is review. We're pulling back to the first derivative test. And my goodness, right now, what are we going to be checking? Well, f prime of x, well, we could have a 3 out in front. It's that 3, x plus 1, x minus 1. Let's go ahead and do some testing. We can test x equals 0, x equals 2, x equals negative 2. And if I were to plug in a 2, we'd get something positive, positive, positive. That would mean that our f function is increasing. Plug in a 0, we'd get positive, positive, but then something negative. Positive and positive times a negative is a negative. That means our f function is decreasing there. And then let's see what's happening when we plug in our -2. Plugging in -2, we'd get this is positive. -2 plus 1 is a negative. -2 minus 1 would also be something negative. A negative times a negative is a positive, times a positive is a positive. So on that interval, we'd have something positive. So hopefully you can see what's happening. Right now, we know where we have maximums and minimums. But let's find out what's happening at those particular values. Like at f of 1, you'd get 1 cubed minus 3 times 1 is 3, plus a 1. Well, 1 plus 1 is 2. 2 minus 3, you'd get a -1. Hey, what if I go ahead and if I plugged in a -1? Well, -1 cubed would be a -1. -3 times a -1 would be a +3. And you could see very quickly, this would be a 4 plus -1, this would be a 3. So right now, we actually have a very good idea where our maximums and minimums are. Look at -1. At x equals -1, our function goes up, then it comes down. That's a maximum. So I could say there's a relative max of 3, always name that y value, at x equals -1 because f prime changes from positive to negative. Similarly, we can say there's a relative min at x equals 1. Take a look at this, connecting the down and up. We can say there's a relative min of -1 at x equals 1 because f prime changes from negative to positive. Well, that's all well and good. That's all well and good. We're definitely moving ahead here. So, look, there's more to the point, though. We should see if there are inflection points. We should see what's going on with our actual concavity. So let's also investigate the second derivative. The second derivative, well, the derivative of 3x squared, you'd get 6x. And the derivative of -3 goes away. If I set that equal to 0, it only takes a moment for us to get x equals 0. That's our prime candidate for having an inflection point. X equals 0 is where f double prime is 0. Let's test x equals 1. And let's test x equals -1. And of course, kids will say, where are we testing it? We're going to test that in f double prime. Plug in a 1, 6 times 1, that's something positive. What does that mean? Our function is concave up. F is concave up there. If I plugged in a -1, -1 times 6 is a -6. That's something negative. That means my function is concave down like a frown there. What are we really getting at? We're getting a change in concavity. We're changing from concave down to concave up. So that means there's a point of inflection. F of 0, if I were to plug in f of 0 and do that right up in here, f of 0, just plug in x equals 0, you get y equals 1. So I'm going to say there's a point of inflection at the point 0, 1 because f double prime changes from negative to positive. Now here's the awesome part. Right now we could go ahead and make a graph. We really could. We could make a real quick graph here, and we know that there's some interesting occurrences with x over here at -1, 1, and also 0. At x equals 1, we're going to be down here at a y value of -1. At x equals -1, we're going to be all the way up here at 3. And at 0, we're going to have 0, comma 1. So what do we know is happening here? You know, right now you can say, well, I know my curve is increasing, and then it starts decreasing when it gets to x equals -1. That's going to be your relative max. And we're going to be concave down like a frown until x equals 0. So look, I don't know exactly what's happening in particular with all these other y values, but I sure can give a really good idea as to what's happening on our curve. I'm even showing the curvature. This is concave down like a frown, all the way up to x equals 0. But then what? You continue to go downward until you get to x equals 1, and then you start increasing. Your curve starts going up. But you're also going to be concave up like a cup. So what's that going to look like? Well, it's going to look something like that. I can check my curvature, where I'm concave up, where I'm concave down. I can see where I've got a relative max, I've got a relative min. The inflection point, very important point because it's telling you where the curvature changes. And guys, that at the heart is how you can use the second derivative to help you proceed and go ahead and get a lot of information on the graph. We're going to stop here and then wrap up with our last page. Actually, we haven't even finished this page just yet. Let me introduce the second derivative test and then we'll proceed to our next video since we've got a moment. The second derivative test, I think the big misunderstanding that kids will have is they'll say, well, you just did the second derivative test with the number line here. I mean, look, you found out where the second derivative was 0. You plugged values in. Isn't that the second derivative test? Honestly, no. The second derivative test is a way not to really check for inflection points, but it's a way to check if there's a local max or a local min. By the way, the College Board will force you down the road to use the second derivative test. They'll give you problems where you won't be able to use the first derivative test. We'll talk about that in due time. But how does it work? It works like this. If f double prime is continuous, look at bullet point number 1 here. If f prime of c equals 0, and kids will say, that sounds like the first derivative test, or at least finding a critical number. Yeah, it seems to be that way. But there's more. What if you know that f double prime of c is greater than 0 there? You could think, well, okay, put them together. What do you now know has to happen? Well, f double prime greater than 0, this is concave up. And f prime of 0, f prime of c equals 0 is a horizontal tangent. So putting that together, take a look over here at this picture in blue. What you're really saying is you've got a concave up curve, but you also have a horizontal tangent line at x equals c. What does that really guarantee? It guarantees that you have to have a local minimum. You put those two facts together and that's what you have. By way of comparison, if you had a horizontal tangent line, a slope of 0, f prime of c equals 0, but you were concave down instead of concave up, well, then your picture would look something like what you have off to the right. By the way, I've been doing calculus for decades. I really have. I've been teaching it for decades. And, you know, just letting you know this, I still, when I'm doing a second derivative test, I make a picture like this. Even to this day, I'll just say, okay, I'm concave down, and I've got a horizontal tangent line. I look at this picture. I'll say, hey, that's the top of the mountain. That's a local max. Previously, we would have had the bottom of the valley. So we have yet to do the second derivative test in this lesson. We're just laying the foundation here. This is how it can be done. Of course, take a look at number 3. If the second derivative is 0, then there's no conclusion. Then you have to use the first derivative test. We'll pick up soon.